So the next important concept is about unsold theorem. Unsold theorem. Take note. Unsold theorem. Listen, what is this theorem states is that the sum of probability distribution function, right here, the sum of probability distribution, sum of the probability distribution function, sum of the probability distribution functions for a given value of L, for a given value of L, where L is nothing but azimuthal quantum number. Okay, for a given value of L and all values of ML. And all values of ML. All values of ML. Okay, is a constant. This is what we call as the unsold theorem. This quantity is a constant. Okay, sum of the probability distribution functions for a given value of L and all values of ML is a constant. Okay, what is meant by this? Listen, suppose I'll take some value of L. For this L, what are the allowed values of ML? I'll take some value of L. For this, the allowed value of ML are plus L, then you have to subtract 1, 1, 1, 1 and goes to 0. Then it will ends with the minus 1. Okay. For a given value of L, there are different values of ML possible. Suppose I'll take L is equal to 1. For L is equal to 1, what are the values of ML possible? ML values plus 1, 0, minus 1. You know L plus 1 will give one state. We represent this as L1, ML plus 1. This represents a state. Then L1, ML0, L1, ML0 represent another state. Then L1, ML minus 1 represent another state. Now take the probabilities of these. Okay, how to take these are wave function. Okay, spherical harmonic function. Take the square modulus of this function and add them. Isn't it? Take the square modulus of this function, then square modulus of this function, and square modulus of this. Okay, called probability distribution function. Add them. This value is a constant. It is a constant for a particular value of L. What is the constant? This constant is actually equal to 2L by 2L plus 1. I'm sorry, 2L plus 1 by 4 pi. Take it. This is what we call as unsold theorem. Okay, take it. In the given problem, L value is 1. So if you put L equal to 1 here, 2 into 1 plus 1, so I'll get 3. So the constant value for this particular state, right, for this particular quantum numbers is 3 by 4 pi. Now we'll do how to calculate average distance of an electron, okay, in any state psi m. Okay, yes, how to calculate. Take it. To find average value, we can use this formula, average value of R. Okay, in any state psi m is equal to A naught by Z. This formula is applicable not only for hydrogen atom, it is also applicable for hydrogen-like species. Okay, and we get 3n square minus L into L plus 1. Take down this formula. This is the question. Find the average radius for 2p orbital of hydrogen atom. 2p orbital of hydrogen atom. Yes. Do it. Then, yes, see, this is the general formula to find the average. A naught by 2 into Z into 3n square minus L into L plus 1. Now we should find out average value of R. Right, now tell me what's the answer? average value of R for the 2s orbital of hydrogen atom. How to find radial node and angular node. Number of radial nodes equal to n minus L minus 1. This is the formula we use to calculate number of radial nodes. Okay, then next one, number of angular nodes. Angular nodes means nodal surface. Nodal surface. Okay, the formula is L. Total number of nodes. Total means sum of radial plus angular. Total number of nodes in an orbital. If you sum up these two, I will get the formula is n minus 1. Take this, very, very important. Someone tell me, what is the number of radial node? Okay, question is this. Find the number of radial node in 1s, 2s, 3s and 4s orbitals. Yes. So, number of radial node, very good. Number of radial node, right? For 1s orbital it is 0 because n minus L minus 1 0. 2s orbital 1, 3s 2, 4s 3, correct?
4s 3.
Yes. So for s orbitals, radial node is nothing but n value minus 1. Okay? N value minus 1 will give you radial node. Because for s orbital, L value is 0, therefore there is no angular node. So the only node that is available is the radial node. Therefore, this value and this value are one and the same. Okay? Calculate number of radial nodes in 2p, 3p and 4p orbitals. Yes, do it. What are angular nodes? Angular nodes is nothing but nodal surface, right? Angular node where the surface where the probability of finding electron is 0. It's called angular node. Okay, directly listen, L value will give angular node. L value will give number of angular nodes. Number of angular nodes. Right? L value will give number of angular nodes. Listen, if you take s orbital, for any s orbital, whether it is 1s or 2s, 3s, whatever it is, for any s orbital, L value is 0. Therefore, for s orbital, there is no angular node. For s orbital, there is no angular nodes. For s orbital, no angular nodes are possible because L is 0. Right? If you take a p orbital, okay, say for example 2px, 2py, 2pz, or 3px, 3py, 3pz, whatever p orbital you take, for all the p orbital, L value is 1. So there should be one angular node exist. One angular node exist. Okay. We say that for for p orbital there is one node available. Suppose if you take say a 2px orbital, 2px, I'll show you. Listen. Suppose I'll take this as x-axis, this as y, and or I'll take this as x, this y, and this is z. This is the usual notation, right? X, y, z. This is positive x and this is negative x. Right? Now I'm going to draw 2px orbital. Observe carefully how 2px orbital look like. It has two lobes, one in positive x side and another one in the negative x side. Hello, Sundar? Now I'll show you a nodal plane here. The orbital is present, the lobes are present to the x-axis. Now I am going to draw a plane in YZ. Okay, in the YZ axis. See? I am drawing a plane in the YZ axis. That plane passes exactly at the middle of the two lobes. We have one lobe in the front side of x-axis, it is positive x, and another lobe in the negative x. And the plane is actually passing in between the two lobes. Are you able to follow? Therefore, this plane is called a nodal plane. This plane passing through y-axis and z-axis, so it is called YZ plane. YZ plane is the nodal plane. And only one nodal plane is possible, only one nodal plane. So that's the meaning for one angular node. For 2px orbital, YZ plane is the nodal plane. For 2py, hello? Can you tell me?
XZ.
Yeah, very good.
XZ plane.
So, let me write. See, for in general for 2px orbital, 2px, 3px, whatever it is, npx. In general for npx orbital, right? YZ plane is the nodal plane or nodal surface. YZ plane is the nodal plane. For any npy orbital, 2py, 3py, whatever it is, for any 2py orbital, right, xz plane is the nodal plane. And I have only one nodal plane, okay? We have only one nodal plane. Similarly, for any pz orbital, we have xy plane as the nodal plane. Okay, so for any p orbital in general, we have only one nodal plane, so it has one angular node. Are you able to follow? Now let me move on to d orbital. In the case of d orbital, suppose I will take n dxy orbital. This may be 3dxy or 4dxy or 5dxy, whatever it is. Right? For dxy, how many lobes possible? Okay, listen. There are two nodal planes possible. Two nodal planes. How? Let me show it here. See, suppose I will take this axis as x and this axis as y. Z is perpendicular to the paper. Just imagine like that. Z is perpendicular to the paper. How we draw dxy orbital? It has four lobes. One in between plus x plus y. This plus x, this plus y. Another lobe is between plus y and minus x. Another lobe is between minus x and minus y. Here. And another lobe is between minus y and minus x. Here, this is positive, this is positive. Positive into positive is positive, so this lobe is positive. Here, positive into negative is negative, so this lobe is negative. Negative and negative is positive, this lobe is positive, and this lobe is negative. Now we have four lobes. See, now I can keep a plane like this. See, observe carefully. I can keep a plane. Okay, I can keep a plane like this. This plane, see, it passes through z-axis. Z-axis is perpendicular to the paper. It passes through z-axis as well as to the y-axis. Okay, so it is a YZ plane. And what about this? I can keep a plane like this, correct? It passing at the center, right? It's called XZ plane, right? So, dxy orbital has two nodal planes. What are they? XZ and YZ planes. YZ plane. So, it consists of two angular nodes. dxy orbital has two angular nodes. Similarly, dyz has two angular nodes. Similarly, dxy, xz, it also has two angular nodes. Right? The nodes are the nodal planes. Angular node means nodal plane. The nodal planes are passing exactly at the center where probability is 0. Okay. Listen, these two are very special. What are they? I'm sorry, the last one. Last one is
square minus y.
Dx square minus y square is simple, but the other one, so okay, let me write dx square also. Dx square minus y square first. How the orbital look like? See, this is x-axis, this is y-axis, z-axis is perpendicular to the paper. Listen, then now for dx square y square, the orbitals are present in the positive x and in the negative x, and in positive y and negative. It is all the lobes are present along the axis, right? Along the axis. Now we have a nodal plane here. I'll show you. I'll show you a nodal plane. So this is a nodal plane, mirror plane. If I keep a nodal plane here, if I keep a plane here, that plane passing exactly in the middle, and the nodal plane does not touch the curves. Does not touch the curve. It is actually passing exactly at the middle. So this is one nodal plane. Similarly, I have one more nodal plane here. So dx square y square orbital also has two nodal plane. It has two angular nodes. Okay, the next example is very important. ND Z square orbitals. This is
இந்த ரெண்டு பிளேனும்